Hey guys, in this particular problem I'm going to cover a pretty challenging problem which utilizes the mechanical energy formula which we've gotten so accustomed with so far in the previous videos. And it's actually a very challenging problem, so I'm going to split it into two different videos, potentially three, so I'll give you guys a really clear understanding step by step of how to solve a problem of this nature. Alright, so here's our problem. Let's say that we've got two blocks, block one on this friction on this hill which has friction, and we've got this block two being suspended in midair, right? And let's say they're being held up at this point, but let's say at some arbitrary time we just decide, hell, let's just let this block two go and watch it fall 2 meters. And once it falls 2 meters like that, let me draw this. Once it falls 2 meters, like that, then we're asked to find what is the velocity of our second block as it falls down those 2 meters, right? And before I get started on the mathematics of it all, let's work on some intuition here. If our second block falls down 2 meters, that would then imply logically that our first block has moved up the slope 2 meters, right? They're connected to a rigid rope, right? The rope doesn't stretch. So this block has moved up 2 meters as well. And let me draw that right here. This block has moved up 2 meters as well. And I'll even draw 2m, 2m here to indicate that they've moved the same distance. Okay, well, let's see if we can figure something else out. We also know that the velocity of our second block must be equal to the velocity of our first block, right, when it falls 2 meters, right? I mean, if it, and you can prove this mathematically as well, but you should be able to validate that using your intuition as well. Alright, well, now that I've got some intuition covered, let's see if we can focus on the mathematics of solving this particular type of problem. And the first step with any dynamics problem, and as I've hammered so many times, is always draw a free body diagram. So let's do that. Let's draw a free body diagram of our mass 1, of our block 1 right here. So this is our block 1 right here. Made it slightly larger so you can see. Right? Let's draw the forces acting on this block. Well, we know there'll be a force due to gravity. It'll be going directly down, right? Not only that, maybe I scrolled too far down. There'll also be a force, which is the normal force, which is always going to be perpendicular to our path, right? And that's going to be our normal force. And let me just write this in. This is going to be m1g, and this is going to be n, our normal force. Not only that, but we're also going to have a tension force in the rope. This is the force trying to pull the block up due to M2, right? So this is going to be our tension force, which I'll just label T. Not only that, but we've also got a friction force which is going to be trying to resist the motion which is trying to pull it up, right? And depending on whether the block is in motion already or whether it isn't, our friction force will vary. I should say our maximum friction force will vary, right? So, but first, we're only considered with whether the block is going to move. That's our first step. Like, the block can't fall 2 meters if it's not moving. So we need to concern ourselves with the static coefficient of friction first. So we're going to concern ourselves with mu Sn to first determine whether, in fact, the block is moving up the hill. Okay, well, now that I've got that sorted, let's see if we can do a free body diagram of our second block too. Well, you're going to have gravity involved. That shouldn't be too much of a surprise by now. And this will be m2g, right? Not only that, but we'll have a tension force too. The same tension force as before because the rope is massless. And that'll be of magnitude t. I hope that makes sense. All right. In fact, let me scroll down so you can see that full force vector. Okay. Well, those are the forces acting on our particular blocks, which are in fact the most important piece of information we can say at this particular point. But there are going to be a few other forces. In particular, there's going to be a force, a normal force on the pin, which is going to be in that direction too, roughly. Okay. Well, I don't want to focus on that too much now. Let's focus on the blocks. And let's see if we can figure out whether, in fact, the block, or M1, is actually moving up the hill. And we've done this before, but I've only done one video on it before, so I really want to make it really clear. And let me just write it down if I can. Alright, let's first make the assumption that the block isn't moving. And then what I'm going to do is I'm going to test the validity of that assumption and see whether that assumption is actually valid or not. So assume for now, assume that block 1, that is the block on the hill, that block 1 is not moving up the hill, i.e. that friction is enough to prevent movement of our block from going up the hill. So and this is really important. This is an important assumption to make. Assume that block 1 is not moving up the hill. Now I'm going to dedicate my time into determining whether this assumption is valid or not, right? And we can do this quite easily now that we've made this assumption by doing this. Let's first calculate the force analysis on block 2. So let me just do that real quick. This is block 2. Let's do a force analysis on block 2 under this assumption. Block 2. Alright, well, there's only one direction the forces are acting, so we can just easily write that the sum of forces in the y direction, are going to be equal to 0. Consequently, m2g is going to be equal to t, right? And this is only true for this assumption, right? If the block was moving, then this assumption might not necessarily be true, right? I mean, the block could be accelerating downwards, right? Alright, so that's under the assumption. What else is true under this assumption? Well, let's figure out what are the equations relevant for block 1. And let me underline that. Alright, well, in order to do this, what we really need to figure out is another coordinate system. Let's define a coordinate system. Let's call this our tangential direction, and let's call this our normal direction, and then do the sum of forces in those directions. So I'll call this the tangential direction, and I'll call this the normal direction. Now let's do some analysis. Alright, well, we know that the sum of forces, and let me scroll down. We know that the sum of forces in our tangential direction are going to be equal to 0, right? And we also know that the sum of forces in our normal direction are going to be equal to 0 under the assumption that we've made earlier, right? Well, in order to do this, what we need to do first is redescribe our force due to gravity on our first block in x and y in our tangential and normal components. So this is our force due to gravity in our normal component, and this is our force due to gravity in our tangential component, right? And just so you don't get confused thinking that these are separate forces, I'm going to do them in dots to show that they're just basically redescribing our force vector, our gravity vector that we already had going earlier. And this is, of course, a right angle, right? But we also know that this angle right here is theta, implying that this angle here is 90 minus theta, implying that this angle here is theta. And using trigonometry, we know that the value, and let me just rewrite this is getting a little bit cluttered. This is m1g. So that implies that using trigonometry, this is just going to be m1g cosine theta, and this is going to be m1g sine theta. Alright, now that we've re-expressed our force due to gravity in our tangential and normal directions, let's see if we can do a force balance on them. Alright, let's scroll back down. Well, what are going to be the sum of forces in, well, which one do I want to do first? Let's do normal direction first. What are our sum of forces in our normal direction? Well, we've got our normal force, that's unsurprising, but we've also got our component of gravity in our normal direction as well. So we're just going to write n is going to be equal to m1g cosine theta, because that's the component of gravity, of our force due to gravity, in our normal direction. So that's another really important formula which you're going to use. And let me just highlight these really quick so I know how important they are. Alright, well, that's one equation. Now let's use the sum of forces in our tangential direction is equal to 0. Well, what are our forces in our tangential direction? Well, we've got our tension, T, acting up the hill, and that's going to be equal to all the forces acting down the hill, which is going to be equal to our friction force, mu Sn, plus our component of gravity in our tangential direction, which is going to be m1g sine theta. sine theta. Alright, well, using all the information we've gathered in our other equations, we can simplify this down. In other words, we can say t is going to be equal to mu s times n, and we figured out n, it was m1g cosine theta, m1g cosine theta, plus m1g sine theta. Alright, and this is the tricky bit, because what this equation really tells us is an upper limit for which the block will not move up the hill. Right? I want to make this clear. This is just an upper limit for which the block will not move up the hill, because our friction force, mu s n, is actually a maximum friction force. This denotes the maximum value of t that can be had in order for the block not to move up the hill, right? But in fact, there are other values of t for which the block won't move up the hill. In fact, if our tension force, and you can imagine this intuitively as well, if our tension force were any less, right? Imagine a smaller tension force. Imagine trying to pull the block up with less force. That means the block will also not move up the hill, right? So in other words, there are other ways to validate this as well, saying that if t was also any less than mu s m1g cosine theta plus m1g sine theta, then the block also won't move up the hill. So this is really just a more generalized expression for saying that these are all the values of t which happens for which the block doesn't move up the hill, right? And we're going to test whether this inequality actually holds true or not. And if it doesn't hold true, that means our initial assumption is wrong. So let's focus on this. And to do this, we need to solve for t. And we figured out t earlier was m2g under our assumption, right? So that means m2g must be less than mu s m1g cosine theta plus m1g sine theta in order for the block not to move up the hill. This is the inequality that must be true for the block not to move up the hill. So let's test whether this inequality is actually true, and by now you should probably have a sneaking suspicion that it isn't, but let's let the math do the talking. So what's m2g? Well, m2 was just 30, right? So that's just going to be 30 times 9.81, which is going to be 294.3. Fortunately for you guys, I've done this question earlier, so I know what all this is. I won't waste time by plugging into a calculator in front of you. And on the right hand side, we're going to be given with 166.06 newtons. And this should be newtons on the left hand side too. Alright, well, tell me, based off kindergarten maths, is 294 less than 166? I don't think so. So consequently, this inequality is not true. As a result, our initial assumption is not true, meaning that our block does in fact slide up the hill, right? Our block does in fact slide up the hill. Alright guys, I think that's enough for this particular video. I'm gonna split it into probably 2 or 3 parts. Now that I've covered, the intuition behind this problem, and I've also proved that the block is moving up the hill. In the next video, I'm actually going to legitimately apply the mechanical energy formula. Bear with me.